So good morning and welcome to my presentation. Today we are going to start a new chapter which is global climate change. So climate change itself a very vast and wide subject matter and where it is written as global, so we can understand that the impact of the climate change is can be observed globally. It is not a local issue. Actually, it is all over the country and all over the area. We can have different sets of impacts of climate change. So this is as it is a very vast issue. So uh, maybe it might not be possible to include all the aspects of the climate change in this chapter. um, and we are going to discuss only few important aspects of the global climate change. We could not discuss here about the different other sectors, which is also very important for climate change or changing aspects. For example, the adaptation and mitigation are two important aspects of the climate change, and that we cannot cover in here because of the very small amount of the time. So what we are going to discuss in this chapter, in this under this title, we are going to discuss about the science of the climate change. Basically, in doing so, we are trying to make our concept a little bit vast about the climate change. And when we say climate change, that time it should also obvious that we are saying that the changes of the different climatic parameters that has been changed during course of times. And as we do not have much of the instrumental data sets before 200 or 150 years before, we do not have any reliable data sets. So to how can we say that that the climate has been changing? So scientists do one things, they construct the past climates. And how do they construct the past climates? We are going to discuss in this chapter. And then we are going to see the possible causes of the climate change. That includes three different things. Because normally we do say the causes of the climate change are very anthropogenic in nature, but climate change actually can be also possible through some natural drivers. And 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 if you do not say that, there is something which you cannot normally, we don't say it's climate change, but we do say that there are a couple of natural variability we can observe in the atmosphere, and that also influences our weather pattern and climatic condition of each of the locations, and that is called internal mechanism. So all of them are related to climate change or climate variability. So we are going to discuss in details the basic causes of the climate change and natural variability. And the later of this chapter, we are going to discuss about the impact of the climate change only on the coastal and wetland issues. There are many different impacts of the climate change, but we are not going to in details of each of them, and it is not also possible in these very short classes. But in your syllabus, this is only we are going to discuss about the impacts of the climate change on coastal and wetland. So before we starting very widely, just to make some understanding about the climate and about the climate change, what do you mean by that? Sorry. Climate normally do say this is a condition of the weather phenomena, and this is the average of weather phenomena for a couple of years, maybe at least 30 years. When do we say climate, we could understand this is as long as 25 to 30 years average of a certain climate variables. What are the variables? Variables are the temperatures, precipitation, humidity, sunshine, and many other things. So those variables are also can be give you different sets of value during course of time, during different seasons, and during different time periods of a day. Such example is maybe you do have an average temperature. If you say any particular location, if it is 20 degree, what does it mean? Maybe in that particular country in the winter they have 5 degrees centigrade. Maybe in the summer season they have much more, for example 30 degrees centigrade. So what does 20 degrees centigrade means? So it also sometimes confusing. So we need to try to understand that what does it mean. So these also varies from day to day, season to season, and many others. So it should be better to say that, for example, in case of temperature, we could say the maximum temperature and minimum temperature. And it is also obvious that in the winter period, the maximum temperature is something which is much more greater in case of summer season. So summer season maximum and winter season maximum is different. And we should say maximum because when we do say average, so it means both the maximum and minimum average, because in the night time that the temperature drop down relatively very lower, and then in the daytime the temperature also increases. So that's why it has been said that when we do say that average, that regards or that corresponds many of the ideas. So that's why climate itself means the average of a particular variables in particular time sets and particular time periods, and also season and everything together. Now, when you say climate change, first of all, the question is it changing really? So, even it is changing, how can you say that? How can you understand the changes is obvious, it is happening? Because changes in the temperature, it is very natural. So today is 25, tomorrow is 26, next day is 23. So how can I say the changes? It's not a climate change, it's a very natural phenomenon of the weather. So when you do say climate change, then keep in mind that this is also should be described in a statistical term, or on the basis of the statistical understanding. What does it mean? It means when you do say change, this change should be basis on a on a basic reference points. What does the basic reference points? For example, what was the condition last 100 years? Okay, so there is a chronological data sets of last 100 years. And now, not today, but from today to another 30 years or last 30 years, we do have some sets of data. So now there is two sets of data, last 100 years data. Maybe from, if I just to say that from 1900 to 1990, so all the 90 years data you have, and from 1990, from 2020 you have another 30 years. So think about what was the condition first 90 years, and then what is the condition of the last 30 years. And now if you just see or make some correlation between these two data sets, then you will see if there is a very big difference among them, significant difference among them, or if they correlate, then how they matches to one another. And then you can say, well, this is a, here I can see some changes that first 90 years the changes is like this, very smooth, so they don't actually changes, they are actually remaining very smoothly and steadily. And then last 30 years the changes is very sharp. Then you can analyze the changes between two patterns or two time periods, and then you can say that climate is changing. So you need some data sets of the past climates, and then these past climates will say you whether your climate has been changing in recent times or not. This is all about. And now, as I discussed before, that we have only the reliable instrumental records for 150 years only. Before that, we do not have any reliable data sets. So, so how can you know that what was the conditions before 180 years before, or 500 years before, or 1000 years before? Some might be argued that, well, even we don't have any instrumental records, maybe it could be possible that these changes, what we can observe now, it was also happened 1000 years before. Okay, and then
Sir, we have fossil also, sir. Fossils.
sorry,
Sir, can't we determine the climate by using fossils?
I'm going there. I'm going there. Thank you. Thank you. I'm going there. So how can we predict that? Someone said that, okay, last 500 years before, it could be possible that the same changes also happened 500 years before, maybe. So we need a very basic, very reliable confidence on our argument that no, there was no sharp that changes we could found there. Similarly, another two important thing is time periods. Time periods is too much important because we do believe that the scientist found or observed that this world has been created 4.5 billion years before, and within this time period 150 years is nothing. And scientists also say that the human being are very much well established, or the presence of the human beings that can also be found not more than millions years before, 2 millions before. So within these time periods, how we can say that climate has been changed because of the human activities? So depending on the data set, we can say that, and that data set can be only possible to create indirectly, not directly. And those systems or those indicators which we can use to construct these data sets is called as proxy data sets or proxy indicators. And these proxy indicators shows us among how climate, what was the climate condition of a particular time periods. So those sources could be ocean and lake sediments, ice cores and glaciers, coral reefs, tree rings, cave deposits, boreholes, and documentary evidence. Yes, obviously the fossils included here, most of the tree rings, which is sometimes also coming from the fossils, they can also be encountered under these sources, because they also give us the idea about long time period ago. So these are a couple of important sources from where we do get information about a particular environment of a particular time, and then we can reconstruct them with the models, and we do have a very good data sets of the past climates. These information of the past climate, we say paleoclimate. So this paleoclimatic knowledge is very much important for climate change science. So now I'm going to discuss few of them, and couple of them we are going to see in the video in YouTube, so that our understanding could be much more clear. So before we going to see that, some ideas should be in our mind. First of all, ocean and lake sediments. We know the anything we can create it, or anything has been eroded, that ultimately goes to the ocean. And ocean floor is a deposition of the constantly burning these older materials, and that also include the aquatic animals and also different planktons inside under the water. The interesting thing is the most of the bones and shells of these aquatic animals, they are constructed with calcium carbonate. And here is the main one. The carbonate itself contains the oxygen molecule, and this oxygen is the most important information center from where we can determine our past climates. How can we do that? Just a very general idea. I'm not very going to very deep enough, because this is not the case. We wanted to very go inside, but but try to understand a little bit. Oxygen molecule, oxygen and oxygen, the atomic weight of oxygen is 16 normally, but sometimes it could be 18. But they are very low amount of the uh, atomic weight 18 oxygen. Uh, and both of these isotopes of the oxygen can remain in the ocean water, and and certainly they have been incorporated into the shells and bones of the aquatic life under the ocean. And when they died, they're gonna be on the ocean floor. And now if we can go under the water, and then we can take the materials from under the sediments, because ocean layer is settled down one after another, and as there is no interruption in there, so they remain for long time as it is. So there is no interruption, and maybe if you dug it, then some sediments you can get from the under the ocean floor, maybe for before 1,000 years, before a couple of thousand years before, you can get the same amount, same bones and sediments which has been buried, which has been layered by the sediments. And how can we know that from that information? Because we know that water containing of oxygen 16, that means atomic weight 16 oxygen, that evaporates more rapidly than O18, oxygen 18, that contain the atomic weight 18. So during glaciers time, the ocean that has been relatively glaciers, when glaciers is starting to grow, that time the relative high ratio between oxygen 18 atomic weight and oxygen 16 atomic weight, the ratios relatively should be high. Why? Because the oxygen 16 water is removed from the ocean, and then these they are deposited as snow onto the growing ice sheets, and that way the ratio of the oxygen 18 and 16 gives you an idea about the condition of the temperature of that time. And then just think about, if you go layer after layer and you get many different values for these ratios, oxygen 18 and oxygen 16 all together, when you found these ratios and corresponding them to a particular sets of temperature data sets, then you can get a series of data sets of the past climates. And this is one of the way that give you the idea about a certain time period, about the temperature of that time. Similarly, you can get the same information from the ice cores. Ice cores, normally this is what the scientists do. They drill an area. Sometimes it is extended to 3 kilometer under the ice, and then from the ground to 3 kilometer down, and then they take a core from there, because that core has not been melted out during last maybe couple of thousand years. And when they were deposited, that time they also contained some oxygen, because that is solid water actually. So H2O contains some oxygen, and that oxygen nature gives us the idea about the oxygen 18 atomic weight and oxygen 16 atomic weight. And among the ratio, we can again found the temperature condition about that time. What about the coral reefs? Coral reefs is another sources from where we do get this information. For example, coral reefs are basically grown in the shallow water sources, not very deep water. So in the shallow water, when the coral reefs grows, and after couple of years, after certain times, they are going to die. And within this time, again, some coral reefs has been grown up on the top of that particular coral reefs. And with the impact of the temperature and other chemical composition, growing coral has been affected, and they have changes their chemistry, and they can be successfully grow in a particular locations. And whether the depth of each of them, then we can determine that the time period when it was started to grow, and that time what is the condition of the sea level of a particular areas. And from that particular sea level and other information, we can also again construct some temperature variations. So not only that, there are a couple of other things from where we can grow on our knowledge about the construction of the past climates. For example, some boreholes temperature profiles we can create, from where we can see the temperatures under the ground. Under the ground means it could be soil or it could be ice cores. So when you go to the top of the ground to the downward, the temperature generally increases in a smoother way. Particularly, it is most or more or less 30 degrees centigrade for per kilometer, because it is going to further to the core of the world, or core of the earth. So it has been increased, and suddenly it has been changed some of the natural phenomena that causes the shifts, and again it can start it to sharp the lines further downward. And the changes itself, when these changes happened, so from the ground which was started, that has been interrupted, and you can analyze that what was the particular time period that has started these changes. And negative inversely, if you correspond that things, why these changes has been happened with, what are the temperatures that corresponds with that, so you can analyze the temperature variations in that particular time. So it is the inverse way to understand the temperature variation. We're going to see that in the video. Rather than that, we can study the pollen in the deep sea ice caps, or in the sea sediments, or in the any deposition of the soil. We can analyze them. We can have certain geological evidence from changes, ancient coral beds, sand dunes, or fossils. We can see the changes in the water level, which is closed in a basin lakes. We can find out any documentation from where it can be a good evidence of the droughts, flood, or crop yield, or rain, snow, or frozen lakes. But that is also limited to a particular location, and the source should be very reliable if we find that. And again, not only oxygen isotopes, but also other type of isotopes, heavy hydrogen, deuterium, ratios in the ice cores, or sometimes nitrogen, different isotopes, or argon also sometimes, different isotopes of argon. So they are also evident of the reconstruction of the past climates. So now we are going to see some videos where it can be discussed very nicely about the process of climate change, past climate reconstruction, from the boreholes and from the sorry, not this one, and from the tree rings, so that we can understand it, how it has been constructed and how do we get information of the past climates. Let's see. Mm, let's see this one.
Another form of proxy temperature measurement is called borehole temperatures. So what you do is you drill a hole in an ice sheet or in a soil column, and you measure the temperature as a function of depth. And what is happening with the temperature is that it's in the equilibrium. If the temperature at the surface stays at a constant value for a very long time, the temperature will just increase with depth because of the generation of heat in Earth's surface. This is called the geothermal temperature gradient. The temperature goes up by about 30 degrees centigrade per kilometer in the Earth, and more or less. So then if you have a sudden change in the temperature at the surface, it takes a while for that news to to diffuse down into the ice core or the rock column that you're measuring. So what would happen to the temperature inside is initially it would only know about the warming right up at the surface, and then as time passed, the temperatures would relax toward a new equilibrium where it's again along the geothermal gradient, just going monotonically upward from the surface condition. So if you go out and you measure the temperature today and you happen to see something that looks like that, you can use what's known as an inverse method to try to back out how much the temperature changed and when. It's called an inverse method because, you know, while reality goes from cause to effect, the change in temperature at the surface leads to this distribution of temperatures below. The inverse problem has to go the other direction and go from the effect, which is this snapshot of temperatures in the boreholes down inside the ice sheet, and sort of back out what the cause was, how much the temperature changed and when. So in general, borehole temperatures give you a much smoother estimate of how the temperatures change with time, because if the temperature changes just a little bit, you know, there's fast temperature changes here, you'll never see that down in the interior. So basically what you see is the longer time scale overall patterns, as we'll see when we put this together.
So this is about the boreholes. How can we measure that? Now we are going to see some tree rings. From tree rings, how can we get the information of the temperature and the precipitation? Because tree rings are a very important source, and they can give us very good amount of the data sets. And throughout the world now, it is also well accepted ideas about making some history or data sets of a particular location.
For families learning, and by subscribers like you. Thank you. Okay, so how has the climate changed around where I live or where you live? To answer this question, we get to go outside. Outside! And look for one of these, a stump. Everything we need to know is right here in the stump's tree rings. Tree ring. So I'm sure that you guys know that trees grow a new ring every single year. Here's kind of what that looks like. But the really neat thing is that the thickness of that ring is determined by what the weather was like the year that it grew. If it's a warm and wet year, the tree will grow a lot and you'll get a nice thick ring that looks like this. But if it's a cold and dry year, the tree's not going to grow that much, and the new ring's going to be much thinner, kind of like this. Trees grow thick rings during warm and wet years and thin rings during cold and dry years.
So important thing is when you get maximum amount of the sunshine with high amount of the rainfall, and you get a good amount of the rainfall, then your tree grows, ring grows very wide. And again, during the opposite, when you do not have much rainfall and temperature is lower, then tree ring is very smaller. And another thing is, it is also determined by from the center to that one, the ring should be growing very smaller and smaller, because at the very first time they grow very high, and similarly their growth should be very slow. And changes of that particular types will answer your question that why a certain change has been happened.
Thick rings, warm and wet, thin rings, cold and dry. And if you think about it, we can use this information to read the tree's rings and learn how the weather has changed over time in the forest where the tree is growing. Did things get colder and drier or warmer and wetter? Were some years one way and other years another? Well, let's figure it out. Let's dive into these rings. We're going to start with this fine example that I plucked right from outside. The one thing to keep in mind while reading tree rings is that trees grow kind of like a lot like humans. They grow very fast when they're young, like a child. Like a small baby child. And they grow much more slowly when they're adults, like how humans grow more slowly when they're old people. So what that means is a tree's rings are naturally going to get skinnier over time, and it's going to kind of look like this. This is what a normal stump should look like ring-wise. You got your thicker rings in the middle and your thinner rings on the outside. What we got to do is to look for the differences, like the rings that don't really follow this pattern. Looking for rings that are thicker than expected or thinner than expected, like these two right here. These are the years the weather was different. It wasn't really normal. So paying attention to those can help us understand how the weather has changed over time. So we'd expect the rings to be thicker in the middle and to get thinner and thinner as we move towards the outside of the stump. But on this stump, there are two spots where it doesn't follow that pattern. Instead of getting smaller, here and here, the rings get thicker. These differences are very subtle, and it helps to look up close. So you got thinner rings over here to thicker rings over here, which means that these rings grew during years that were warmer and wetter than usual. And here's an even bigger stump that I checked out. It has 64 rings, so it was 64 years old when it was chopped down. It has thicker than expected groups of rings here, here, and here. Even more evidence that things are warmer and wetter than usual. So, if I had to guess how the weather might be changing around me, based on these tree rings, I'd say that on average, it's getting warmer and wetter. And the neat thing is, that's true. Here are two confusing graphs that show just that. That Chicago, where I'm from, is getting warmer and wetter, thus confirming our tree ring results. So trees are kind of like climate time capsules, which is helpful because in a lot of places, scientists have only been taking weather records for like 100 years or so. But now they're studying the rings of trees that are thousands of years old, which can help them figure out what the climate was like way before they were even taking those records. So hey, I got a